Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss about the module Metal Oxide Semiconductor Field Effect Transistor MOSFET from the paper Electronics. So students, let us see what we are going to learn in this module. First, enhancement mode MOSFET, E-MOSFET will be discussed. Second, types of MOSFETs will be discussed. Third, detailed IV characteristics of MOSFET will be discussed in this module. So students, let us start with a basic introduction about the module. These devices, the MOSFET, are used for VLSI, very large scale integrating circuits such as microprocessors, semiconductor memories, and power devices. MOSFET is also called by many names like IGFET, insulated gates, MESFET, metal insulated semiconductor, metal oxide semiconductor transistor, MOST. So, it is the unipolar transistor which act as a voltage controlled device where current at the two electrodes, drain and source, it is controlled by the action of electric field at another electrode gate having in between the semiconductor and metal a very thin oxide layer. Enhancement mode MOSFET. Let us now discuss the schematic of N-channel E-MOSFET or enhancement mode MOSFET. So students, this figure shows the schematic of N-channel MOSFET having metal gate electrode which is electrically insulated from semiconductor, N-channel, P-channel semiconductor by a very thin layer of insulating material or oxide, usually silicon dioxide. Gate terminal is isolated from main current carrying channel so that no current flows into the gate. It consists of a p-type silicon substrate into which two heavily doped N+ regions have been diffused, namely source and drain. They have been clearly depicted in this figure. Metal contact is deposited on the oxide layer that covers the gap between two N+ diffusion and it serves as the gate. Students, now there are some important parameters in order to characterize the device. That is, in this schematic, L is the channel length, or we can say the distance between two N+ P junctions. Z is the channel width, D is oxide thickness, and Na is substrate doping, which is almost or usually p-type. So the central section of the device corresponds to the MOS diode and source is used as the voltage reference. It is also called as the 4-terminal device because of two N+ regions, source and drain. In p-type silicon metal contact on the oxide is gate. Let us now discuss the case when some gate voltage or Vg is applied. When Vg is 0, source to drain electrodes corresponds to two N plus P junctions connected back to back. So here the only current that can flow from drain to source is reverse leakage current. So initially the device is off when Vg is 0 and a sufficiently large positive gate voltage greater than Vt has to apply to induce a channel below the oxide, that is a surface inversion layer is created, which is clearly shown in this figure. The electron concentration in the channel and hence its conductance can be modulated by Vg, back surface contact or the substrate contact can be at reference voltage with source or is reverse biased. The back surface voltage will also affect the channel conductance. Let us now discuss the working of MOSFET. When Vg is greater than Vt, it causes inversion at semiconductor interface. So if small Vd is applied or the drain voltage is applied, electron will flow from source to drain through conducting channel. Here the channel acts as a resistance and Id is proportional to Vd, which is shown in this figure by the linear region. As long as Vd is small enough, the surface potential will remain almost same throughout the channel, that is near source and drain regions. The electron concentration will remain the same and it behaves as a resistor having R equal to L by sigma A, where it is equal to minus L by mu n Z Qn, where Qn is less than 0, Z is the channel width and Qn is nothing but the electron charge per inversion area of the inversion layer. Now, as the increase in Vd, the potential will distribute throughout the channel due to uniform and moderate doping with Na of P substrate. So, source and substrate are connected and are grounded. The potential difference between the gate and the inversion layer will be more near the source and very less near the drain. Therefore, electron concentration will decrease near drain and hence R increases. So, in the IV characteristics, as discussed previously, there will be a bending downward from the initial linear curve. So, if further increase in Vd, the potential drop across the oxide near drain will continue to decrease until it falls below the value required to maintain an inversion layer, that is width of inversion layer xi at y equal to L reduced to 0, or we can say this as the pinch off point. Here drain gets isolated from conducting channel inversion layer by a depletion region. So the ID will then saturate to a constant value Vd equal to Vd saturation at ID saturation. Now if we are increasing the Vd, that is Vd is greater than Vd saturation, ID remains as ID saturation and the pinch-off point will move towards the source and effective channel length L prime will decrease. However, the potential at P will remain at VD saturation and additional voltage in excess of VD saturation will drop across the depletion region. Thus, number of carriers arriving at point P, which was shown previously, from source and hence current flowing from drain to source remains the same. So if there is an increase in Vg to Vg2 or Vg3, there will be an increase in the inversion layer charge Qn. Therefore, channel resistance R decreases or ID increases for a given Vd as shown in this figure, and the pinch-off point will occur at a higher value of Vd. This is related to off-channel case when Vg equal to 0 or no channel in normal case. Students, let us discuss the types of MOSFETs depending on the type of inversion layer. So there are 4 types. First, N-channel enhancement, normally off. Second, N-channel depletion, normally on. Third, P-channel enhancement, normally off. And lastly, we have the P-channel depletion, normally on. So, if Vg equal to 0, channel conductance equal to the low value to depletion, it is low, that is, apply Ve greater than 0 to form N channel, that is normally off enhancement mode, and here Vg is greater than Vt for a particular value of Id. Now if Vg equal to 0 and if channel inversion layer exists at 0 bias due to low Na concentration in p-type substrate and presence of phi ms and positive charge in oxide, then the device is normally on depletion N-channel MOSFET. So here large current can flow at Vg equal to 0 and the current can be decreased by applying negative Vg, more depletion, or increased by applying positive Vg enhancement. Similarly, we have a P channel which is normally off enhancement and normally on depletion MOSFET. Let us now summarize or discuss the IV characteristics of the MOSFET in detail. Here we consider the ideal conditions and following assumptions, that is, gate, which implies the ideal MOS, that is no charge in oxide and phi ms equal to 0. Next is the current flow in Vd, that is there is no current flowing from source to drain. Third is electron mobility in inversion layer channel is constant, independent of electric field. Doping in channel is uniform. Reverse leakage current is negligibly small. Gradual channel approximation is valid and is generally true for long channel MOSFETs. This implies transverse Xi-x, that is perpendicular to the current flow, at the edge of the depletion region in channel is much larger than the longitudinal Xi-y parallel to the current flow. So this figure shows the input and the output IV characteristics of MOSFET. Now consider the N-channel MOSFET So the total charge induced in semiconductor at Y is Qs equal to Qn plus Qsc, where all these are functions of Y, and Qs is the charge per unit area in inversion region, and Qn is the charge per unit area in the depletion region. So if we apply Vg, that is partly divided in oxide and semiconductor, that is Vg equal to V naught plus psi s y, or we can write it is equal to minus Qx by C naught plus psi s y. Now in the case of non-ideal MOS capacitor with flat band voltage, previous equation is modified as Vg minus Vfp equal to minus Qs by C naught plus psi s. So if we put the value from equation 2, that is the equation for charge, the total charge, we have C naught multiplied by psi s minus Vg plus Vfp equal to Qn plus Qsc. Now substituting the value or getting the value for Qn, we get Qn equal to C naught multiplied by psi s minus Vg plus Vfp minus Qsc. Let source and substrate are connected and consider a strong inversion condition, that is no drain current flow in a MOS, so system is in thermal equilibrium, that is Vd equal to 0. So the surface potential psi sy is equal to 2 psi b at the onset of inversion. Under practical operating condition, space charge region in MOS transistor is not in equilibrium, that is, when Vd is greater than 0, the surface potential will increase with Y due to potential distribution in semiconductor. If Vy is channel potential at any point Y for a drain voltage Vd, then to a good approximation, the surface potential for strong inversion is psi s inversion equal to 2 psi b plus V as a function of Y. Also using depletion approximation, the charge per unit area QSCY at strong inversion is QSCY equal to minus QNAWM, approximately equal to minus root of 2 epsilon s QNA multiplied by V as a function of Y plus 2 psi B. Since V as a function of Y increases with Y basically, so QSCY increases with Y from source to drain. So now putting the value of psi sy and QSCY from the equation of psi s inversion and QSC in the equation for Qn, we get Qny, that is Qn as a function of Y, equal to C naught multiplied by 2 psi b as a function of Y plus V as a function of Y minus Vg plus Vfp square bracket close plus root of 2 epsilon s Qna multiplied by V as a function of Y plus 2 psi b. Let us now consider a small element dy in the channel. So for a constant mobility, the resistance of small element dy of the channel is dr equal to minus dy by z mu n qn as a function of y. Therefore, voltage drop across the element of resistance dr due to drain current id is dv equal to id dr, which implies id multiplied by dy equal to minus mu n z qn as a function of y dv. Now substituting qn as a function of y from the previously discussed equation in this equation and integrating from y equal to 0 to L and v equal to 0 to Vd. So your IDL equal to minus mu n z c naught bracket the integral 0 to Vd 2 psi b as a function of y plus v as a function of y minus Vg plus Vfp multiplied by dV plus root of 2 epsilon s qna by c naught multiplied by integral 0 to Vd over root of 2 psi b as a function of y plus v as a function of y dV bracket close. This implies that ID will be equal to plus mu n z c naught by L bracket Vg minus Vfp minus 2 psi b minus Vd square by 2. This whole is multiplied by Vd minus root of 2 epsilon s qna by c naught multiplied by 2 by 3 multiplied by the bracket 2 psi b plus Vd to the power 3 by 2 minus 2 psi b to the power 3 by 2. So this is the ideal MOSFET equation if we remove VFB from this equation. Now students, let us consider the two types of regions. Here we will be discussing about the linear region. For small Vd such that Vd is very much less than Vg minus Vt or Vd is very much less than Vg minus Vfp plus 2 psi b and Vd is very much less than 2 psi b. We have the previously discussed equation as Id equal to mu n z c naught by L bracket Vg minus Vfp minus 2 psi b. This whole is multiplied by Vd minus root of 2 epsilon s qna by c naught multiplied by 2 by 3. This is multiplied by 2 psi b to the power 3 by 2 multiplied by 1 plus Vd by 2 psi b to the power 3 by 2 minus 2 psi b to the power 3 by 2. So this is equal to mu n z c naught by L bracket Vg minus Vfp minus 2 psi b. This whole is multiplied by Vd minus root of 2 epsilon s qna by c naught multiplied by 2 by 3. This is multiplied by 2 psi b to the power 3 by 2 multiplied by 1 plus 3 by 2 Vd by 2 psi b. So here we have done the Taylor expansion minus 2 psi b to the power 3 by 2 bracket close. So now this is equal to, after simplification, mu n z C naught by L bracket Vg minus Vfp minus 2 psi b multiplied by Vd minus root of 2 epsilon s Qna by C naught multiplied by root of 2 psi b Vd bracket close. This is equal to mu n z C naught by L Vg minus Vfp minus 2 psi b minus root of 4 epsilon s Qna psi b by C naught multiplied by Vd. This is equal to mu n z C naught by L bracket Vg minus Vt bracket close multiplied by Vd. Now here we have assumed Vt to be equal to Vfp plus 2 psi b plus root of 2 epsilon s Qna 2 psi b by C naught. By plotting ID versus Vd graph for small Vd, Vt can be obtained from linear extrapolation to Vg axis. So for n-channel MOSFET, VFB is small, negative, and other terms of equation 13, which was previously discussed, are positive, implying Vt less than 0, turn off voltage, to turn off the MOSFET by depleting the channel. So equation 12 implies ID is proportional to Vd for small Vd. So in linear region from equation 12, we have the channel conductance as Gm equal to del ID by del Vd at constant Vg equal to mu n z C naught by L multiplied by Vg minus Vt. And the transconductance Gm equal to del ID by del Vg at constant Vd equal to mu n z C naught by L multiplied by Vd. Let us now discuss the saturation region when Vd increases such that the inversion layer charge Qn equal to 0 at y equal to L, that is number of mobile electrons in channel at the drain, are reduced drastically, or we can say this as the pinch off point. At this point, Vd equal to Vd saturation and Id equal to Id saturation. For Vd equal to Vd saturation, we have a saturation region. So therefore, V as a function of y equal to Vd saturation and Qn equal to 0 at y equal to L. Then in the equation for Qn, we are putting this value. So we get 0 equal to C naught multiplied by 2 psi b plus Vd saturation minus Vg plus Vfp bracket close plus root of 2 epsilon s Qna Vd saturation plus 2 psi b. So 2 psi b plus Vd saturation minus Vg plus Vfp equal to minus theta multiplied by Vd saturation plus 2 psi b, where theta is equal to root of 2 epsilon s Qna by C naught. So we'll find out the Vd saturation from this equation and substitute Vd equal to Vd saturation in equation 10, and we can obtain Id in saturation, that is Id saturation. However, considerable simplification of equation 16 occurs when Na is very low and oxide layer thickness is small, that is C naught is large. So under this condition, theta is very much less than 1 from 17. Now here voltage drop in oxide is negligibly small compared to 2 psi b. Thus equation 16 becomes Vd saturation equal to Vg minus Vfp minus 2 psi b approximately equal to Vg minus Vt. Now putting the value of Vd equal to Vd saturation in equation 10, we get Id equal to Id saturation as Id saturation equal to mu n z C naught multiplied by bracket Vg minus Vfp minus 2 psi b minus Vg minus Vt by 2 bracket close multiplied by Vg minus Vt minus 2 by 3 theta multiplied by 2 psi b plus Vg minus Vt to the power 3 by 2 multiplied by 1 plus Vd by 2 psi b to the power 3 by 2 minus 2 psi b to the power 3 by 2 bracket close. This is equal to, after simplification, mu n z C naught by L bracket Vg minus Vt the whole square minus Vg minus Vt the whole square by 2, which is equal to mu n z C naught by 2L Vg minus Vt to the power 2. So this is the square law dependence of Id on Vg, same as in JFET, and it is valid for all Vd greater than Vg minus Vt. So the channel conductance for ideal MOSFET in saturation region is 0. Transconductance in saturation is given by Gm equal to del Id by del Vg at Vd equal to constant equal to mu n z C naught by L multiplied by Vg minus Vt. Now here this Gm is same as Gd in linear region, which was signified by equation 14. Students, let us now discuss the effect of substrate bias. Now when Vb is applied to the substrate with respect to the source, then psi s prime y equal to 2 psi b plus V minus VBS during strong inversion, and Qn changes to Qn prime as a function of y. Now here we replace 2 psi b with 2 psi b minus VBS in all the expressions which were discussed previously, and Vt is replaced by Vt prime. Therefore, substrate bias shift the threshold voltage to a new value. So at higher frequency, consider the capacitive coupling between the device terminals, CGS, which is the MOS capacitance, and it considers the frequency dependence, which will be discussed in the later slides. Now, from this frequency equivalent circuit, we get that the Ft, that is the frequency, is the frequency at which the ratio of input I output to I input becomes unity. That is, the device can no longer amplify the input signal when output of MOSFET is short circuited. So this is known as the operating frequency. So Our aim is to find out this frequency. Now from this circuit, at higher frequency, we consider the capacitive coupling between the device terminals, that is CGS is the MOS capacitance given by ZLC, where C is equal to C naught Cj by C naught plus Cj, and CGD is the gate to drain capacitance, provide undesirable feedback between input and output. So from the circuit, the input current is Im equal to 2 pi Fr multiplied by Cgs plus Cgd multiplied by Vg equal to 2 pi Ft Cg Vg, where Cg equal to C naught ZL equal to epsilon naught ZL by D, where C naught is the capacitance of oxide and D is the thickness of oxide layer. So output current is I output equal to Gm Vg. So substituting the expression for Im into I output, the cutoff frequency is Ft equal to Gm by 2 pi Cg equal to mu n C naught Z Vd by L 2 pi C naught ZL. This is equal to mu n Vd by 2 pi L square for Vd less than Vd saturation. For high frequency and high speed operation, short channel length L and high carrier mobility is necessary. So students, let us summarize what we have learnt in this module. First, we discussed in detail about the enhancement mode N-channel MOSFET, E-MOSFET. Second, various types of MOSFETs were also discussed. Third, we derived the relationship between the voltage and the current for MOSFET and studied the detailed IV characteristics of enhancement mode MOSFET. Thank you.